Thank you very much, Jules. Okay, very excited to be here. I'm Don. I work as a developer advocate here in London, and I basically help developers build apps on Android. And I'm very pleased to be joined by Phil.
Yep, so my name is Phil Burk, and it's a little bit ringy. I work in the Android framework group in Mountain View, California.
Right, so I'm extremely nervous about this because like loads of things can go wrong. But we hope today to live code a synth from scratch, asterisk, some copy paste might happen. We're going to demonstrate a new API called Oboe, which is an open source library which can be used to build high performance audio applications. And we'll also show you how you can obtain this elusive low latency on Android. So we're going to build an app. Starts with an oscillator. Does anyone not know what an oscillator is? Good. It's going to produce a sine wave. We're going to build an audio engine. And that's going to be responsible for creating an oboe stream, and that's an audio data stream. And this is using this new oboe library. That's going to be responsible for talking to the Android audio framework, and ultimately, it's going to pump data out of the inbuilt speaker on this Pixel XL device. We need some kind of, and when the stream needs more data, it's going to send a data callback into our audio engine, and then it's going to, the audio engine is responsible for supplying audio data back into the stream. So we have this loop of callbacks and a data being supplied. We're going to have a UI, and that's going to send touch events down into a JNI bridge. Now, our UI is going to be built in Java, but our audio engine and all the other aspects of the application are going to be built in C++. So we use JNI to basically translate between Java and C++. That's going to be sending this tone on, tone off event into the audio engine and ultimately into the oscillator to turn it on and off. Don't need to explain what an oscillator is. That's good. Okay, so let's get started. So I have Android Studio here. I'm going to start a new project. Let's just call it ADC'17. Includes C++ support, so Android Studio now has great C++ support. We specify our API, and this determines our device coverage. So we will specify API'17, which gives us 99.2% coverage. We will have an empty screen just for our UI. Keep the defaults as for the activity name and our layouts. We can specify either C++11 or C++14 as our toolchain. And this is now going to trigger Android Studio to create a template project for us. So this is creating the UI, creating the layouts, and creating us some default C++ files. So if I click on project here, so inside here we have Gradle scripts. So Android uses Gradle as its build system. And the first thing I'm going to do is change my app's build configuration to specify only the architecture for this device. So by default, Android will build for x86, x86 64, ARM7, ARM8, and a couple of other architectures, which is great if you want to release your app on a multitude of different architectures. Not quite so great when you have about 35 minutes to build a synth from scratch and you don't want to wait minutes for it to compile. So I'm just going to add a filter here, ARM64v8a, and then I sync to just get it to rerun the build. The other thing I'm going to do is change my CMake build script, or rather build configuration. So we use Gradle for the Java side and CMake for the C++ side. So here's one I prepared earlier. So the first thing we do is we include and build our oboe library, which is an open source library, which we'll talk about in a few minutes. I'm globbing my app sources, so that's going to pick up all the C++ files in my project. I'm going to give my library a name, and I'm going to add some dependencies. So the main ones here are this oboe library and OpenSLES, which has been the standard on Android since, I think, API 9. And so we include this as kind of a backup API if oboe can't use the latest APIs. So that should be about everything we need to build this project. So if I just hit run now, you'll see that my Pixel device is connected, and we should get a blank project. So it's now installing the APKs, and I'm told that if I hold this exactly in the right place, we might be able to see the app. Not much to see at the moment.
The split screen.
There we go. OK. We have a working app. Hooray. So,
not yet a synth, an app.
So I'm going to add an oscillator. And as I said, this is the only part where I'm going to cut and paste this. So I've just got an oscillator that I prepared earlier, which I'm going to copy in. I will resync project. Now, our oscillator has a few methods, but the main one here is render. It's difficult to see.
Back to full screen.
Great.
We're good.
So this is going to take an array of floats, and the size of the array is specified by num frames. We iterate through this array, and we're going to populate this array with our sine wave. So we have a frequency for the left channel of 440, middle A, frequency for the right channel of 659, middle E, so we get a perfect fifth. Just render the samples into this array. So that's what we need to do there. Now I'm going to create my audio engine. Okay, so I've got a header and an implementation file created for me already. I'll just sync this. And the thing I'm going to do here is include this oboe library. There we go. I'm going to have a single method called start. And I can create the definition for this method by holding down Option and hitting Enter. And then Android Studio has all these lovely autocomplete methods. So now I can start using this oboe library. But before I do, Phil's going to explain why we should use the oboe library and why it's such a fantastic project.
Okay, so why use oboe? There's several API options in Android, the Java API, there's OpenSLES API, and now we've added essentially 2 more APIs. So the first reason to use oboe is that you can write less code. And here, for example, is the OpenSLES code for opening a stream. And now if we look at this top here, we go through, no, I'm not going to have to go through this code. There's no point in looking at it. No one really knows what this does. Everyone just sort of puts wrappers around it. So that's the code to open a stream in OpenSLES, and this is the code to open a stream in oboe. So we're using a builder design pattern. You can set options if you want, and then you can open the stream. And typically the defaults are enough, but that gives you an open stream. So it's arguably a bit easier to understand. Another reason is that A-Audio is the place we're putting all the new features. So we can't really change OpenSLES that much. It's a standard API. Whereas A-Audio, it's Android Audio, and we can change it and well, we can't change it, we can add to it and improve it over time. So that's where we're focusing our new development efforts. So oboe is a direct mapping to A-Audio. So if we add something to A-Audio, oboe can use those features. Another reason to use oboe is that oboe is open source. So if there's a bug in Oboe, we can fix it immediately and get the fix up there in a few days. It's also a place where people can contribute suggestions and make improvements very, very rapidly. So I think also what Oboe does basically is it provides a wrapper over AUdio and OpenSLES. So Oboe calls the operating system API for AUdio, and if that's not available, it will fall back and use OpenSLES. Is the slide?
Next one.
This next. Okay, this is good. So your application at the top calls Oboe, and if you're calling to Oboe on new devices, which is Android O and later, it can use AUdio, and on Marshmallow and Lollipop and KitKat and all the way back to Jelly Bean, it can use OpenSLES automatically. So if you just write to one API, which is the simple C++ API, you can target all 99.2% of the Android devices. And on the new devices, you'll automatically get the benefits of AUdio. So back to live coding.
Okay, so to create a stream using Oboe, we need a builder. And then we can use the builder to set properties on this stream. So there's all sorts of properties that we can set, but we will just set 2 of these. The first one will be the format. And I'm going to specify it as float. The other format we could specify would be 16-bit integers. And I'm going to set the channel count. We have a stereo oscillator, so it figures we're going to have a stereo output stream. So once I've set my properties, I can do builder, open stream, and that requires a reference to a stream. Again, in Android Studio, if you see something that's red, if you press Option and then Enter, it gives you a list of things that you can do to solve that problem. So I'm going to create a new local variable called stream. Okay, so now that the stream is open, I can query that stream by doing stream.get, and then we have a whole load of properties which we can obtain from that stream. The one that I want to obtain is the sample rate. Now, I want the sample rate because if we have a look at our oscillator, the phase increment is dependent on the sample rate, as in the oscillator needs to know how fast we need to generate samples. We'll just resync as well, because it looks like it's not picking up this audio engine file. So back to the implementation. So I haven't yet declared an oscillator in our audio engine, so I'll do that now. Just call it MOSC. Auto include that. I'll just tidy this up as well. So we want this to be a public method. Okay, so now we can do MOSC set sample rate and just set the sample rate on our oscillator. And now we can asynchronously start our stream. So this will start the data stream out to the audio hardware. But so far, our oscillator isn't linked to our stream. So the next job is to link the oscillator to the stream using this callback mechanism. We do that, again, using the builder. So we're going to set callback, and that takes an Oboe stream callback object. And I absolutely love this shortcut here. So what I want to do is have my audio engine extend from Oboe stream callback. So I just specify this here. Now it's the red line underneath is telling me that that this object doesn't extend from Oboe stream callback. So if I just hit Option Enter, it will allow me to actually have it extend Oboe stream callback. So if I look in the header now, it's extended automatically. I now want to override one of the methods in Oboe stream callback, so I use Control O, and it's the onAudioReady method that I want to override. And this is going to be called every time the stream wants new data. So we get a void star of audio data. Now, it's a void star because the format can be 16-bit integers or it can be floating points, so we're going to static cast it back to being an array of floats. If I can type. Okay, and then we're just going to call our render method. Okay, there we go. Let's get rid of that. The other thing we need to do is we need to return a result here. We can either return a continue, which will tell the stream, hey, I'm going to be sending more data after this, or we can send a stop, or return a stop, which will stop the stream. So result continue, get rid of that. Now, what am I forgetting? I'm forgetting to turn the oscillator on. So we'll go set tone on true here. As yet, nothing is calling our start method. So I'm going to go into our JNI bridge, which is called native lib here. And we have this, this template method, just a string from JNI. It means nothing. You know, you can rename it to whatever you like, but it is called on startup. So I'm just going to borrow this method to sort of, for my own purposes, create a static instance of my audio engine. And we'll just call engine start in here. And let's run it.
Yeah, you just go back to audio engine CPP. You type set sample rate instead of set tone on.
I did. Thank you very much, Jules. Audience debugging. This is great. Okay.
File on Android bug report. We'll get to it in a couple months.
Okay. Hopefully, if I hold this, we have a sound. A synthesizer. Okay, I cheated with the oscillator, but so we have a sound, but we have no control, and you know, really we do need some form of control for our synthesizer. So let's add some control. To do this, I'm going to go into Java land, into our main activity, which represents our screen. So our main activity is able to receive touch events from the screen, and in order to do so, we have to override a method called onTouchEvent. And that gives us a motion event, so this could be touching down on the screen, lifting your finger off the screen, or dragging across the screen, and a number of other gestures. The ones that we're interested in are the touch down event. So we get the action and just test whether it's down. And then we're going to have a method set tone on. So we're going to call this method, which is going to ultimately set the oscillator to be on. And the other case is motion event up. And that's going to switch it off. Okay, again, it's red. I'm going to create a method. Now, by default, it thinks that I want to create this method in Java, but actually I don't. So I'm just going to remove this and declare it as a native method. Now, this native method hasn't been defined yet, but again, I can do this. Now, this is super helpful. Like, if any of you have ever used JNI, you'll know that the method names are ridiculously verbose. So to have to type out Java, com, example, don, all that, you know, I'd be over my deadline for this talk just by writing out that method name. So it creates it automatically for me, which is super helpful. So we're just going to have another method on our engine called setToneOn, pass through this Boolean. And we'll create a new function. Now, it hasn't quite got this right, so I'll just correct the method signature to something like that. And now if we go set tone on is on, and rerun, I've made a deliberate mistake here, which is I've forgotten, okay, so it's still on. I forgot to switch the oscillator off when I called the start method. But if I tap down now and lift off, it should switch the oscillator off. So, okay, so now we have our control.
So you're already a virtuoso on this instrument.
It's just
amazing.
incredible, isn't it? So I wonder what the latency of this synthesizer is, the tap to output latency. So I'm actually going to test the latency. And to do this, I'm going to use the tried and tested method of smacking my finger against the screen and recording that impact, and also recording the output from the speaker and measuring the delta between the two. So I've got Audacity here. I'll just hit record and okay. So you should be able to quite clearly see the finger slap there, and then we have our oscillator being produced there. So down the bottom we have our latency, 102 milliseconds there. I'll just do another measurement, just so you know we've got a number to choose from. Okay, 113, perhaps one more. A whopping 128. Okay.
That seems a bit high.
Yeah, it's a little bit on the high side. Typically we're looking at sub 50 milliseconds from tap to output for these real-time use cases. That's not great. So, Phil, why does this happen, and is there anything we can do about it?
Yes, indeed. So a lot of apps don't necessarily need high latency or low latency. So for example, if you're doing a composing app and you're playing a staff notation score, it's just playing out and you're not interacting with it, so the latency isn't critical. So if you want low latency, you have to turn on and request the low latency. This will give you sort of more frequent wake-ups and puts a little bit more stress on the system, so it's not the default. So what we can do is, the default is no optimization. If you really don't care about latency and you're doing like streaming MP3s off of a server, you can go into a power saving mode where you only wake up every few seconds and dump your audio in. But if you want low latency, you have a low latency performance mode that you can turn on and request that. When you do, you'll could take advantage of maybe the fast mixer, which is in the audio flanger. And if you're on the Android O devices, you can take advantage of a new data path, which gives you a lower latency and higher performance. So this data path has been enabled on Android 8.1, which is the MR1 release, and that's available for preview download from the Android websites, and it's running on Pixel phone. So it's sort of just coming out for a few devices, and then it'll be spreading sort of through the Android ecosystem. But it will still make a difference, even a significant difference, even on older devices if you're using the legacy path.
So if you're using Oboe, you don't have to worry about this. It'll obtain the optimal level of latency as long as you set the low latency mode.
Yeah. And actually, this is all under A-Audio too, which is the built-in API. So I think we're back to live coding.
Okay, so we want to use this low latency mode. Again, we just use our builder. We're going to set this performance mode to low latency. And that is literally all we need to do. So I will rerun our app now. In fact, I've still got the bug, so I'll rerun it. I'll just remove the set tone on from the start method. And okay. So just remember that we were at about between 110 and 130 milliseconds before. Okay, so we're at about 65 on that one. 62 on this one. It is worth mentioning that the screen has between 20 and 30 milliseconds of latency. So what we're really interested in is the output latency on the audio stream rather, there is very little you can do about the actual screen latency. So if there's variance in these latency numbers here, it will come from the screen. The latency through the audio stream should be fairly fixed.
Yeah, it'll vary a couple milliseconds, but the big variation is when you catch the screen scan in its scanning process.
Okay, so we've reduced by, let's say, between 40 and 60 milliseconds just by introducing this low latency mode. But we're still up at kind of 60 milliseconds. I think I had one that was 50, 55 or something like that. It's still, I still feel like there's more we can do. What do you think, Phil?
I think there is. So when you request a low latency mode, you'll probably get a buffer that has a capacity of several bursts. So a burst is what the DSP or the DMA is reading the data in. And that may be on the order of 2 milliseconds, 4 milliseconds. So you may have a buffer that's got 100 milliseconds capacity in it. And if you fill that buffer up to the top, then you're going to have 100 milliseconds of latency from that buffer. But you don't have to fill it up to the top. It's like if you ride around, you don't have to fill your gas tank all the time. You can ride around with a quarter tank. And so what we can do is set our buffer size. The capacity would be, say, 100 milliseconds. We can set our buffer size to be 2 bursts, which maybe would be 4 milliseconds. So, and that's what determines the latency. It's the amount of data that's actually in the buffer, not the potential size of the buffer. So if we do that, we could probably drop our latency down quite a bit.
Okay, let's do it. So after we've opened the stream, we are going to know what our burst size is. This is kind of the minimum size that our buffer could possibly be. So we'll get frames per burst, and then all we do is stream set buffer size in frames. Now, I'm gonna do something reckless here.
Yeah, you're just single buffering here. This is
Normally, we wouldn't recommend single buffering. It doesn't offer much underrun protection, but screw it. Let's just do it like that.
kids these days.
Okay, so rerun our latency test. Okay, so we've knocked another 15 milliseconds. I'll just do another one so it's not an anomaly. 41 and 45, so 15 to 19 milliseconds off there. So we're now at 41 milliseconds tap to output latency. So
And 20 to 30 of that is the screen.
Yeah. So again, the screen is now forming the vast majority, or the majority at least, of that latency. So I have been a bit reckless there by using just a single buffer. And there is a technique that you can use to kind of avoid this recklessness, which Phil's going to talk about.
Okay. Also, say if you're using MIDI, then the latency, instead of having, say, a 20 to 30 millisecond latency from the touchscreen, the latency for the MIDI going through the system can be under a millisecond. So if you're not sure how reckless to be, because when you go out on these different devices, you can't test all the different kinds of Android devices out there. There's just too many of them. But you can start off being optimistic and say, well, let's start with a single buffer. And then you can query to find out if you've had any underruns. And if you have an underrun, then you say, well, let's just bump that up a little bit. So you can go to double buffer or triple buffer. And if you're running for a while without any glitches, you might drop it back down. So you can dynamically tune the latency of your application based on whatever device you're running on in real time. It's best to kind of let things settle out a bit, so don't just set it on the first callback, because it may take a while to get things to stabilize. A couple of callbacks, 2 or 3 callbacks should be fine. And then you can just dynamically in real time be adjusting your latency so that you've always got sort of the minimal latency on the particular piece of hardware that you're running on.
And Oboe has a class called Oboe Latency Tuner, which you can just call the tune method on, and it will do all of this automatically.
Another technique for reducing latency even further now, and this was mostly, in this case, since we're doing the screen touch, we've got a big contribution to the latency from that. So if you won't see much effect from this, but if you're doing like a guitar fuzz effect where you're just doing straight input-output latency, then this can make a big difference. And what you can do is you can bypass the mixer that is in this portion. So the application can then write directly into FIFO that's being read by the hardware. So your app writes it into a FIFO, the DSP or the DMA is reading that data back out, so there's no intervening stages between your app and the hardware. So for that, on that device, that's potentially the lowest latency you can get. We're still working on reducing the hardware latency in the DSP and DMA, which can be 2 or 3 milliseconds in some cases. And if you add USB, that can add 1 or 2 milliseconds as well. But this exclusive mode will get you past the audio mixer and can reduce to the minimal latency. You won't see it here because your latency is varying, 20 to 30 milliseconds from the screen touch.
It might be worth just saying that this isn't like a Google exclusive feature. We're working with OEMs for them to implement this as well, because really this is the path to the lowest possible latency.
Yeah. So this what this does is it uses the mmap no IRQ mode in the also driver, so that you're basically chasing the DMA counter around the loop and just sort of laying audio just in front of the hardware counter, the hardware index. So
let's implement this. Now, as Phil said, we're unlikely to see much difference here because of the screen latency, but for completeness, set sharing mode, and then we want Oboe sharing mode exclusive.
And you can always ask for it. If the device doesn't support it, or if something else already has exclusive access, then you probably just get the shared mode, which would go through the mixer.
And if you ever want to see what your stream has been given, you can always check logcat.
Well, or you can call get sharing mode on the stream that you get.
Yeah, that's probably a better way of doing it, actually. Okay, so whilst you're debugging on a particular device, it can be useful to see just in the logs. And here we have, when your stream is opened, it tells you how many channels, the format to is float, and then sharing is exclusive here. So this device supports exclusive mode, so we have been granted it. So let's rerun our latency test. Okay, there's a few good ones there. Okay, so we are seeing a difference there. That's about 34 milliseconds. I think we're about 40, 45. Could have been an anomaly, but okay, 30, 34, 36. And that is the minimum possible latency from tap to sound output on this particular device. So yeah, there we go. That's how you do it.
So some other results here. This is some measurements that were made using round-trip audio latency, which is done using a loopback connector that takes the output from the headphone jack and just feeds it back in through a resistor back into the device. There's a little thing called a fun plug, and if you really want one, you can let us know. We can email you, or we can't email you one, but we can mail you one. I wish. Some guy asked me once to email him a microphone so that his software would work, and it took me a long time to explain why that wouldn't work. So these are measurements made on a Pixel XL, running the MR1 or the 8.1 version of Android. And this was set with a slightly more conservative 2 bursts per buffer and with the performance mode low latency. So if we're going through the older, this is what we call the legacy data path, which is what the Audio Flinger and OpenSLES and the Java audio track uses, going through that path, because we can do our dynamic latency adjustment and stuff, we can get down 19 point, it'll vary a millisecond, so it's like 19, 20 milliseconds basically, which is in the, what we're calling the pro audio range, where devices can set a pro audio flag. And the burst size, the DMA is reading in chunks of 192 frames, which is 4 milliseconds. So if you're double buffered, that means that just the output buffer itself is about 8 milliseconds. And then it's shared, so there's another buffer below that, which is maybe also 8 milliseconds. And then there's the hardware, and then there's the feedback, the loopback path, and you add those all up, and you get about 20 milliseconds. If you have the mmap mode enabled, which will happen if you're running with MR1, then the burst size will drop to 96 frames, which is 2 milliseconds. And I guess I need to be holding that. And that's available on the Android API 27, and that drops us down to about, well, it'll eliminate 2 milliseconds, so it gets us down about 17. And then if you turn on the exclusive mode, and this was for both input and output, so you're eliminating the mixer on the output, and you're also eliminating one stage of sort of a distribution phase on the input side. And so you can get round-trip latency around 10, 11 milliseconds in that mode. And that's with double buffered. So if you single buffered, you probably get below that. So this is on Pixel phones, which is like this mini phones. And the job this year is to get these sort of numbers spread to the rest of the Android ecosystem. So there's a lot of phones out there that are still at 100, 200 milliseconds. And we're hoping that there's some low-hanging fruit there where you can get them down quickly down to at least 20 milliseconds. Getting them from, that should be fairly doable. Getting them from 20 milliseconds to the 10 milliseconds will require these mmap changes in the kernel and driver changes. But then each millisecond sort of gets harder and harder. But at this point, we're in the range for most keyboard apps. MIDI keyboard apps will perform. They'll feel fine in this range. It's really sort of like input monitoring for voice and guitar fuzz effects and stuff need lower than this. So, but this is good for most MIDI. Even drum pads and stuff can operate just fine in this range.
Cool. So in summary, if you want to develop for Android, please download Oboe, start using it, start filing bugs against it. Thank you all very much.
Excellent stuff. You made it look easy. Any questions? Question just there.
Hello, thank you. Would it ever make sense to develop audio in Java, and what would the latencies be?
It depends on your latency requirements. So Java's probably 20 milliseconds behind what you can achieve natively. So it depends. Like if you can tolerate an extra 20 milliseconds of latency, by all means develop in Java.
Yeah, and if you do, there's a performance mode for low latency in Java as well. And you should request the native sample rate. So make sure it'll probably be 48,000 hertz. If you do something like an odd sample rate, like 44,100, then you'll go through a different path, which has higher latency. So you want to make sure you get on what's called the fast track. But if you do, you can get very close to OpenSLES numbers.
If you're running in Java, do you run into locking problems like mutex problems, GC problems?
The garbage collector used to be sort of a big problem. The old Java garbage collectors, you don't free memory in Java. You just sort of forget something, you just abandon something, and then somebody comes along later, freezes the system, and then gathers up all the things that you left behind. And that garbage collector used to disable interrupts and just freeze the Java machine for 20, 30, 40 milliseconds. It was like big. Now they do an incremental garbage collection, and it's like just on the order of a couple milliseconds or something. So the garbage collector is not the problem that it used to be. So you can actually get quite good performing apps in Java if you turn on this low latency flag and use that fast track.
Any more questions? There's one here.
I was wondering if you plan to add, or does Oboe already got MIDI support in some sort of way, or?
Definitely on the roadmap.
Well,
it's not in there.
Oboe. You're asking if Oboe has MIDI support?
Oh, sorry, right, okay.
That Android got MIDI support, but it's for I think it's API 23, something like that. So
API 24 Marshmallow is where native MIDI support.
No, Java API.
Oh, in Java.
No, you said native, but the API, the Android MIDI API is in Java. You said native. If there's no native MIDI API at this point, but other people have requested native. Were you asking for a native MIDI API?
No, I'm not asking for. I'm not sure about if I care, if it's native or not. But if I plan to use Oboe, for example, and you want to get the shortest path, then I guess I'd like my callbacks to include also my MIDI messages with my audio processing.
Yeah.
Each callback.
So what we do, and we'll be posting a native MIDI synth here pretty soon. What you can do, there's a Java API which will get a callback when MIDI events come in, and you can take those MIDI bytes and put them in a FIFO that is readable by the native code. So then your audio callback just checks the FIFO, and if there's any MIDI data in there, it just processes that MIDI data and turns on the notes, turns off the notes, sets controllers, then renders the audio and returns. So that path, because if there is a preemption or anything in the system, that MIDI event might just get delayed like a millisecond or two, but it won't cause an audio glitch. So we don't have to buffer MIDI events the same way that we need to buffer audio as a protection against glitches. So the MIDI data just flows through the system as quick as it can. And it'll typically be under a millisecond. So the latency, even going through Java, the latency for the Java MIDI is not a significant addition to the latency. You just have to get it from Java, put it through to a native FIFO, and then pull it out the other end. And we'll post an example.
Yeah, so I think what we need to do is, because Oboe is very, very new, and there is just one code sample for it, perhaps if we post a code sample which includes MIDI, which uses the Oboe library.
Yeah, I have one, I just haven't posted it yet.
Okay, thank you.
In fact, I can demonstrate.
There was another question over here.
Hi, I have a question regarding the automatic latency adjustment that you were talking about.
Oh, yeah.
What is exactly the strategy there? Do you use like some kind of interpolation so that there is no artifacts you introduce? And that would be the first question. And the second question, how do you know, like, if you automatically reduce the latency over time? I mean, your only criterion you're gonna get at some point is a glitch, right? And you really want to avoid that, right? So how can you know, like, how can you reduce the latency there?
Right. So that tuning algorithm is a bit tricky. So that's why we didn't put it in the operating system. So the only thing that's in the operating system, there's a couple things. One is you can get the number of underruns. So when you get an underrun, you bump it up. But I think your question is, when do you decide to lower it back down again? Because if you lower it and you glitch, then you lower it and you don't want to be in that mode. So what you can do is you can look at the write counter and the read counter. So if you're doing output, the write counter is what you've written and the read counter is what the DSP has written, and the difference is what's in the buffer. So you can kind of check that, and if you're generally full, then let's say you look and it's like, wow, I've always got like 4 bursts in there. I think I can go down to 3. But if you're monitoring that and it's like, whoa, that was close, almost, and you see that you're almost glitching, then don't lower it because that means you need that buffering. But if every time you check, you're kind of full, it's like, okay, I think it's safe. You go down to 3 and yeah, we're still safe. So you can get an idea of sort of how much safety you have by looking to see how full the buffer is. And if you're running, if you're often going down, then don't lower the latency.
Thank you.
Good. Any more questions? I think there was a hand over there on that side.
Yeah, thank you. How much latency optimization can I get if I use Oboe, but the final backend is OpenSLS?
Oh, I don't. Yeah.
Sorry, I didn't hear the question.
How much latency optimization can I get if I use Oboe, but the final backend is OpenSLS, not A audio?
The latency optimization at this point is only supported on A audio. Yeah.
But it is possible to do it on OpenSLES from, I think, API 25 onwards. There is the mechanism, the underlying mechanisms to support it, but before then, there's nothing.
At least I can get the fast path, right?
Yeah.
Yeah, get the fast mixer, yeah. But it's nice to, sort of allocate a big buffer and then just to have that in reserve and then just set your latency to whatever it needs to be, because you don't want to be in a situation where you're glitching. So if you can do the latency optimization, then you've got the safety of a big buffer if you need it, but you can run with low latency if the device is supporting it.
Okay, we're out of time. There's 10 minutes till the final keynote of the day. So thanks once again to Don and Phil.